So I will tell today about some results which are relatively recent. This is also a result of a collaboration. We like to collaborate a lot. As I told yesterday, after this little brainstorming, we see the collaboration as the most constructive form of competition of science, and we have all the best experiences coming from that. Let me start with a little summary about how this project relates to the Fotonika. So basically this includes myself, who was hired by the Fotonika project, Nikolay Bezuglov, professor from St. Petersburg, Teodora Kirova. He's one of the examples how the project has helped not only to hire a person, but only to promote her. She has now been elected as a leading research scientist at the institute. Kristina Andreeva and Dasbruk Markovsky is actually a couple, married couple from Bulgaria. And we have established a good working collaboration with the institute there. There are also, as an outcome of this project, two PhD students, Martin Bruvelis and Artur Stinic, who shall be defending sometime soon. So, I mean, this project has had a very clear, very measurable impact in terms of people's careers. Yeah. As I said, we love to collaborate, and we have collaboration partners in Taiwan, in Lithuania, in Russia, in Germany, United States and Italy, and the particular results that I'll be showing come actually from the collaboration with the PISA team. The project was also, the Fotonika project, I mean, was also enabler on the technical side. We could acquire some laser systems which gave us much improved spectral resolution for the experiments, and also we tried to use them smartly in a way that we exploited synergy with the laser center, so that we pooled the equipment we acquired via the Fotonika project with the equipment which was already there, so that we can share the actual capabilities, so that everybody is having more, except that of course you have to somehow do the time sharing. So this is one of other positive outcomes, and here the two PhD students, and since we can never have enough of them, so we cloned them so that we have more of them. So about the very experiment, it's actually quite simple and goes to, I would say, very fundamental thing in physics, which seemed to be very well known and nothing unexpected would be coming out of that. Nevertheless, there were some surprises. So here the experiment, we have a cold beam of cesium atoms coming out of a pyramidal magnet-optical trap. When I say cold, it's really cold. The atoms are moving with this velocity of 12 meters per second, so you could actually see how atom is flying. And the velocity spread is something like 1.5 meters per second. So this is really very slow beam of cold, or if you like, ultra-cold atoms. Then they arrive to a zone where we excite resonance transition, which seems to be very well known, how you excite it. Just a simple, with single laser, a resonant transition. And we do probing of the population via photoionization. Photoionization laser is very weak, non-perturbing, and we detect, we apply the electric field and detect the ions with electron multiplier, and this is the measure of the population in the excited state. The level scheme of cesium, again, it's very typical for alkali atoms, nothing surprising here. So we are exciting on the transition from 6s1/2 to 6p3/2. It's 852 nanometer line of a diode laser. And we can excite selectively either F equals 3, F equals 4, or F equals 5, and we always start from the F equals 4 in the ground state. And one small detail in the experiment, we have the excitation laser beam actually is bigger than the probe laser beam, which ionizes and produces the photoions. This is for the simple reason that we are not so very much interested in the linear excitation regime, which would produce a relatively large number of ions, but it would obscure the nonlinear part we're actually looking for. So we try to probe actually in the middle of the excitation laser pulse, Laser pulse is because we have CW laser field, but as the atoms are flying through the laser field, so they are actually seeing the pulse as each atom sees a laser pulse, which is a very long pulse because the beam is very slow. And here are the results. So if you excite F equals 4 to F equals 5, it's probably not so surprising in the very beginning that the signal is growing stronger than in other two cases. But if you look here at the scale, it's actually 2 orders of magnitude. So this is a little bit unexpected. Now, even more unexpected is if you are looking now to the excitation of F equals 4 and F equals 3, you see in the beginning there is kind of expected pattern that the signal saturates and there is some optical pumping, but then suddenly there is an increase, and this was really puzzling. So we tried to understand what is actually happening here from the point of view of fundamental physics. Can we understand that? Now a little bit about the constants involved and how this all happens. So since we do couple unstable excited state to the ground state, and the coupling measure of the coupling strength is the Rabi frequency, then the ground state is actually acquiring a certain width, and this will be the one which will be leading to the optical pumping or to the loss of population out of the ground state if the branching ratio of the transition is not equal to 1. And since we have a very long transit time, which is actually much longer than the time which is necessary for substantial pumping of population out of the system, then actually the critical Rabi frequencies, which translate into the laser intensity, the critical laser intensities at which those effects will be happening, are actually very small. And you can calculate that, and you see that those critical intensities, they are several orders of magnitude smaller than the saturation intensity, which would be classically seen as a measure of a non-linearity in the excitation is kicking in. So we can distinguish 3 regimes of coupling. So we have weak coupling when the Rabi frequency is smaller than the critical Rabi frequency, so basically you have no pumping, linear excitation regime, everything clear, not too interesting. Then we have some intermediate regime when the Rabi frequency is larger than the critical one, but still smaller than the saturation Rabi frequency. This is where we would observe optical pumping typically. And then we have the regime of large Rabi frequencies, and this is where state mixing through the Outler-Towns effect will be coming into the play, and this is actually the one which will be leading to those peculiar observations. So what is the Outler-Towns effect? Just a little lecture from quantum physics. So if you have a 2-level atom, which is described by some atomic Hamiltonian, you couple in a strong laser field. What happens is that you have to take into account this light atom interaction to the total system Hamiltonian, and if you do so, then you are actually obtaining new quantum states, adiabatic states or dress states, whatever you call them, but the essence is that you have mixed in those new states actually this state and this state, so you create the mixtures. So that means if we are shooting with a strong laser field into several hyperfine states in the excited state, if it is strong enough, we'll start mixing those states in the upper state. Yeah, so there will be some effects because of that. So now, since in the experiment what we measure is the ion count, and ion count actually relates with some detection efficiency to the population of the excited state or to the ionization probability. This detection efficiency is not necessarily well known, but we can eliminate that if instead of looking at those total signals, we look at the signal ratios. For example, ratio of a signal when we excite F equals 5 and F equals 4. If we take the ratio, then this thing will cancel out, so we can actually quite cleanly work with something that can be translated from the population of the excited states. So what you see here now is the dots are the experiment. Then here is the simulation, which is full simulation with the density matrix, and here we take into account the Zeeman structure, the many magnetic sublevels which are present. If you don't take that into account, then actually you see that this doesn't really describe the situation well at all. And here, just for reference, this is the ratio of the line strengths. If there was any optical pumping, then this would be basically what you would be observing. But we know that this is not really true, so it's just for reference to see how remarkable the difference is. And it is remarkable, it's 100 times, it's 2 orders of magnitude. Now, if we look at the ratios for the excitation of F equals 4 and F equals 3, then, I mean, this is weird. Because it goes down, then there is some kind of a minimum, it rebounds, then it drops again, and at the first glance you do not really understand what's happening there. So let us try to interpret it somehow. And in order to do so, you have really to go and look into the magnetic sublevel structure. And there are 2 different things happening. So one thing that happens is the formation of the so-called bright resonances. So if you have excitation from F equals 4 to F equals 5, here is the simplified system of the Zeeman sublevels. So what is happening here, you have a smaller number of levels here than you have here. We excite with linearly polarized light, so that means only those transitions are happening. Yeah, so the delta M, the change of the magnetic quantum number, is 0, and they can cascade down here, and they can cascade down to another M level. So in the end, you have some accumulation of population in this central sublevel, from which you can again excite. Yeah, so that's why it is called bright resonance, because you accumulate in a level from which you can bring the population up, and you can see it very well. Now, if you go to states with F equals 3 and F equals 4, here the situation is different. So if you take F equals 4 to F equals 4 transition, what you see is that here we have the excitation, it's delta M equals 0, the selection rule, and you can cascade down to 3 from each of those. You can make 3 transitions to the magnetic sublevels down here. And what you see is that this transition is forbidden. You cannot excite it with a laser because of the selection rules, so there will be accumulation of population here, and you cannot see it. And that's why it's called a dark state. Or, for example, if you take F equals 4 to F equals 3, then you have here a larger number of the magnetic sublevels in the ground state, and you have accumulation of population in those outermost Zeeman sublevels, and these are again dark states. Yeah? So you have actually quite different situation if you look into the Zeeman structure. And let us have a look how these populations look like. So here is the excitation from F equals 4 to F equals 5. So this is when the bright resonance is formed. If we have very small laser intensity, in this case it's just 3 microwatt laser power. So what you see is that actually the population in the upper state is following more or less precisely the Gaussian envelope of the laser pulse. And you see that there is it's 10 to minus 8, so there is really negligible population in the other 2 states, which is this one and this one. And you see that the transition is really cycling. Because this is the population in F equals 3, it just stays the same, there is no pumping into that one, and this population reduces only at the time when the population is up, and once the laser pulse is gone, you have restored the population here. Now, once you increase the laser intensity to 10 milliwatt, the laser power to 10 milliwatt, you see that the peak of the population actually shifts to the earlier times of the laser pulse. Yeah? You also see that there is quite some population now already in the states which is F equals 4 and F equals 3, and this is because what I was telling, there is this mixing of the states due to the Outlet-Towns effect. And as soon as you have population here, you start doing optical pumping. So this means that from this F equals 4 and F equals 3, you can, the population can decay to this hyperfine state of the ground state, and you do not excite from there. And this is what you see here. If you calculate the population, this is the population in this state. So you see that it is actually dropping here, and you see that the population in this state is accordingly growing. And there is a little shoulder here, and this can also be explained because this is at the times when the laser intensity has reduced already sufficiently so that you do not mix any longer those states. So that means you just close the leak channel, and that's why you create such a small shoulder. Now, if we look at what is happening when we have F equals 4, so when we have small intensities, but we have optical pumping. Now in this case, when you excite this transition, this level can decay to this one and to this one, and this one we do not see. I mean, this is the lost population. So we see that in the F equals 4, there is a population only in the early time of the laser pulse, and within that early time you very efficiently deplete the level F equals 4, and you pump the population in the other level. Now, there is some residual population. This is the dark state. This is where they stay, you cannot access it. But when you increase now the laser intensity to laser power to 10 milliwatt, then what you see is that first you have one peak here in the population of the F equals 4 state, and this is the same what is happening here. You like do the optical pumping, and then like it stabilizes at this level where the population has been pumped into the dark state. And now, when you arrive at a site where the laser intensity is higher, so that you are mixing actually the states here. So what happens is that whenever you put an admixture of F equals 3 to F equals 4, the delta M equals 0 for the M0 and M0, I mean, you make that transition allowed because for unequal Fs it's allowed. It's forbidden only for equal Fs. Yeah? So you pump out the population also from the dark state, and this is where the second peak is coming from, and you can actually show that for low intensity, this is now the population of the dark state, yeah? M equals 0. So, for low intensity you pump the population into the dark state, while for high intensity you first pump it in, and then you mix those states, and then you pump it out and deplete it. So this is the dynamics that is happening there. And so now we are actually ready to understand what is happening here when we compare the signals. So you have now here comparison of this excitation and this excitation. Why is it growing so far and so fast? It is simply because this is the bright resonance which is playing the effect here. So firstly, you pump a lot of population into this M equals 0. Yeah? So you go to F equals 5, and in F equals 4 you have a population M equals 0. And now when the intensity is strong enough so that you start mixing F equals 5 and F equals 4, then what happens is for F equals 4, F equals 4, you actually inhibit the pumping of the population out of the bright state, because for equal Fs, as I said before, M is 0 to M is 0 is forbidden. Yeah? So that's why you have this very dramatic increase here. And here the decrease is simply coming because of the interplay between the transition strengths. So this transition is stronger than this one. So this will be, the population will be depleted much faster for transitions to F equals 4 than to F equals 3, so the ratio will be dropping. Then there is a small rebound, and this rebound is because you start accessing the dark states for this transition, but then you start, when you increase the laser intensity even more, you start accessing also the dark states for the other transition. And since in that case you have actually 2 of the dark states, so you have more population that you can pump out, so this will continue dropping down. So we can understand actually, if we look at this, what is happening. And so what we can do is that we can now review in such slow laser pulses and in such slow excitation, very long passage, inner beams which are used, for example, for cold atom lithography. You have several stages. So first, the linear stage when everything is like just linear excitation. That is known. Saturation stage, when there is a notable population depletion. Intermediate stage where you have the accumulation of population in the bright or dark states. And finally, the final stage, and this is the new one that we had through this study, is that in the ultra-town stage, due to the mixing, we are coming to actually some weird effects which have to be taken into account. So, and let me also take 1 or 2 more minutes to tell about my new place where I have moved. And this is again, I would say, as alumni of Photonika project, I would also like to indicate that there are even more possibilities for collaboration. So I have moved to a new university in Saudi Arabia. It's called KAUST, King Abdullah University of Science and Technology. For those who haven't been good at geography in school, Saudi Arabia is the largest country in the Arabic Peninsula, and KAUST is near Tubal, a small fishing town, just at the coast of the Red Sea, some 80 kilometers from the biggest city of Saudi Arabia, Jeddah. Now, the interesting thing is that we have actually quite some good opportunities for making new collaborations. Of course, there is this straightforward possibility that students can come to us and study with us, but we do also have the visiting student research program. This is like in Europe you have Erasmus, so we have a counterpart of Erasmus, where students can come for a limited amount of time, 2 to 6 months. They get their stipends, which are a bit more generous than the Erasmus, and they can work on research projects in extremely well-equipped laboratories, so I think that could be quite some added value for the students here. And also we are in an interesting situation that the university is having internal funding agency, and that funding agency is having collaborative grants, where up to 40% of the funding can go to the external collaborators. And the success rates are something between 30 and 40%, so it is actually not that uninteresting. So that's why I had brought with me some brochures which I placed outside, which is describing actually who are the people there, what are the names, and what are their interests, so that you could actually have a look at it and maybe you'll find a way how you like to collaborate with us. Thank you.